Hello everybody, and welcome to the second MDPI webinar on catalysts, dedicated to bioelectrochemistry. Thank you very much for joining us today. This is the second webinar of this series, based on the special issues and sections from our Catalyst journal. If you are interested in submitting your paper to a special issue, a list of all the open ones is available on the webinar webpage. This webinar will be chaired by Dr. Elisabeth Lojou, with Professor Jens Ulstrup as the main speaker. We will also have a final discussion and a Q&A session moderated by Dr. Elisabeth Lojou. If you have any questions, please feel free to post them in the Q&A box. I would also like to remind everyone that this webinar is being recorded and that we will also have a YouTube live streaming today. The recording will be posted on the webinar webpage for everyone to watch it as soon as possible. Finally, I want to present our chair, Dr. Elisabeth Lojou. She is a research director at the French National Center for Scientific Research in France. She obtained her PhD degree from Paris 12 University in 1988, and after numerous positions at CNRS, she formed the Bioenergetic and Protein Engineering Laboratory, focusing her research on the functional immobilization of redox enzymes onto nanostructure electrochemical interfaces. Her aim is to understand the molecular basis for the oriented immobilization of enzymes on electrochemical interfaces favoring fast electron transfer processes. She has authored over 100 publications and is currently chair-elect of the Bioelectrochemistry Division of the International Society of Electrochemistry and a member of the Council of the Bioelectrochemical Society. I will hand out the microphone to her. Thank you, Elisabeth, for accepting to chair this webinar, and everyone, enjoy.
So thank you very much for this nice introduction. And I would like also to say good afternoon to everyone who is taking part to this webinar. So this is organized by MDPI, and I am very pleased to chair this session. Of course, I hope, first of all, that all of you and your family are in good health. And well, it would be also better perhaps to have face-to-face discussion with Professor Jens Ulstrup instead of this webinar. But I hope also that this type of event, online event, would allow perhaps a nice alternative to traditional meetings and traditional seminars, and will allow perhaps more people to attend this type of seminar, which is also very good. So before giving the line to our speaker today, I would like also to thank particularly Dr. Chen-Chin Xiao from Denmark University, because he was really at the origin of this webinar organization. We both, Cécile and I, have the feeling that it was important nowadays to really try to promote enzyme electrochemistry. And so I just would like to make a short focus on our own scientific activities in that domain. So as it was said before, my laboratory belongs to CNRS and Marseille University, and we are investigating in this laboratory the main bacterial metabolism from a cellular to a molecular point of view. And we are especially studying the way redox proteins and redox enzyme can really exchange electron with electrochemical interfaces in order catalysis may occur. For that, we're looking at different proteins and different enzymes, such as cytochrome cupredoxins, for example, but also hydrogenases, which has a key enzyme for H2 oxidation and H2 production, and also some multi-copper oxidase, such as cytochrome C oxidase, but also bilirubin oxidase or lactases for oxygen reduction. And we are immobilizing all these enzyme and protein on different types of electrochemical interface, which can be either sulfur-carbon monolayer, for example, on gold electrode, made by immobilizing different tiols with different end functions in order to try to control the way the enzyme is interacting with the interface. Or we are also immobilizing this enzyme on more porous films, made, for example, by carbon nanotubes, bearing different chemical function, again trying to really tune the orientation and the way the enzyme is interacting with the electron. So all of that, the main objective is really to try to get the key parameters for an efficient bioelectrocatalytic process, and we especially use this fundamental knowledge in order to try to develop very quite efficient enzymatic fuel cells, and especially the enzymatic fuel cell, which is based on hydrogenase and multi-copper oxidase, in order to try to replace the platinum catalyst in the low temperature membrane proton exchange fuel cells. So to reach this objective of bioelectro rationalization, we will have to pursue in fundamental research and also to try to develop new tools to get new insight at the molecular level of the processes. And today, it is really my great pleasure and my great honor to introduce Professor Jens Ulstrup as a speaker of this webinar. Professor Jens Ulstrup is highly recognized in the electrochemistry community for his fundamental research on electron transfer processes, especially involved in biological systems. He is author or co-author of about 350 peer-reviewed publications. He was awarded the prestigious prize from the Bioelectrochemistry division of the International Society of Electrochemistry, for which he became a fellow. He was also awarded the Julius Thomson Gold Medal for meritorious research in Denmark. So just to mention some of the relevant reconnection features of Jens, clearly highlighting the tremendous research activity in the electrochemical domain. So Jens, we are really very honored to welcome you today in this webinar. And so please now, the internet platform is yours.
Thank you, Elisabeth, for this kind introduction. And thank you to the organizers of this webinar series for the kind invitation to contribute. And certainly thank you to all of you who are listening in the background, so to speak. There's been a slight turbulence about the title of my webinar. This title, which is written here, that is the title. And that's what I'm going to talk about. From single crystal gold to three-dimensional porous electrodes. I'd like to emphasize this is the result of joint efforts by many people, our group here and our partners in other countries. It is sad, of course, that we see they keep on dying around us, but they have contributed very much over the years. And also here are some generous funding agencies who have accepted our kind offers to make good use of some of their research money. I'm going to give some background material first, and then gradually move towards more complex systems and also towards more recent material in our group. Yeah, we can remind ourselves that bioelectrochemistry, in the way we like to know it now, maybe it started about 40 years ago. Here are some of the pioneers, Professor Miki, Alan Hill, and Theodore Kowana. These achievements, they followed what you call an electrochemical renaissance beginning in the late 1970s, where electrochemists discovered physics. They discovered solid state physics and surface physics. So they were gradually able to introduce things like clean electrode surfaces, single crystal, atomically planar surfaces, spectroscopies, not in the least the scanning probe microscopy, atomic force microscopy, and scanning tunneling microscopy, diffraction, electron microscopy, and also electronic and molecular structure calculations of the surface, electrochemical surface, and interspatial charge transfer theory. There is a very nice review by Professor Kolb in Angewandte Chemie where all these are clearly set up. In our group, we use some of these techniques. We use single crystal, clean electrodes. We are able to study bioelectrochemistry of single molecules using the electrochemical scanning tunneling microscopy. And now, more recently, over the last several years, we began to study smart electrode materials, if you can call it that, porous materials with the view of stabilizing and systematically immobilizing the enzymes in new environments. And to this comes elements of theoretical support. If we begin with a clean electrode and gradually work our way up, so to speak, from a single or let's call it 0 dimensions up to 3 dimensions, then this is what the single crystal gold electrodes look like, the 3 facets of the 3 low index facets. This is what they look like schematically from above and from the side. you will see that you can actually see single atoms. But we have to realize that even the single gold electrode has a life of its own, because the surface atoms, they get unhappy because they don't have neighbors on both sides. They have neighbors on the bottom side, but just air or vacuum on the top side. So they have a tendency of cramming together. And we call this phenomenon reconstruction. They reconstruct. And here you can see there's some sort of reconstruction here from the side of the gold 111 surface. There's also the life of its own can be seen electrochemically, because at certain potentials, reconstruction is lifted. That can be at certain potentials or on anion adsorption. So that is very specific for the different electrode surfaces. You can see 111 and 100, and here 110. So if we observe strange electrochemical signals somewhere unexpected, it is not necessarily Faraday signals. It can be capacitive signals, and they can be very sharp if a phase transition is involved. We can also modify the electrodes, as we just heard. Functionalized alkane thiols are very commonly used. They are easily prepared, and they bind to the gold surface via the sulfur atom. And then they have different functional groups in the other end of the molecule. That is extremely versatile. They can be positively charged or negatively charged, neutral, large, small, and they are ideal building blocks for gentle immobilization of proteins, so the proteins can feel comfortable on surfaces such as these ones. They're also key targets in the way of studying how molecules are actually bound to the surface. A core fingerprint of the gold sulfur bond, this is exemplified by the amino acid cysteine. That is what we call reductive desorption. And I'll come back to this in a moment. There is a very sharp signal, provided it's a good surface and a good self-centered monolayer. Very sharp voltammetric peak at a given potential. That's very useful because it can be used to tell us how many molecules are on the surface. We get a sharp peak if it is a good surface. If it's a poor surface, we get a broadened signal. You can see it's specific for the surface, gold 111, gold 110, and some recent data from our group by Christian Engelbrecht, who's sitting next to me here. There are actually two reductive desorption peaks, indicative of two different kinds of surface binding of the cysteine molecules. The actual gold sulfur bond has commonly been represented as a gold 1-thiolate bond. But we know now, we like to believe, there's a wealth of spectroscopic and electrochemical and not in the least computational data to show it is not gold 1, it's actually gold 0. And so the sulfur, the thiol is bonded as a thiol radical. This is the process that is the dominating process in gold sulfur bond formation. And the opposite process, as is written here, that is exactly the reductive desorption. So if this is a one electron transfer process, which we like to believe it is, then we can, from the area under the voltammetric peak, we can calculate the number of molecules on the surface. This is discussed in some recent contributions from our group, you can see listed here. About the studies of single crystal electrochemistry, polycrystalline electrode surfaces can be polished to mirror finish, and no one can see with a naked eye that they are not absolutely flat. But in 200 nanometer resolution, you can see it's a mountain landscape, and no one can see if there should be a molecule there or not. And the voltammograms, I'm not saying all voltammograms of polycrystalline electrodes look like this, but they are often not well resolved. The gold oxidation and the reduction of the gold oxide. Whereas if you go to the single crystal electrode surface, first of all, you can see almost with your own eye, or at least using electrochemical scanning tunneling microscopy, it looks much smoother. Here are some step edges, and here you can see the voltammogram, which looks much prettier than on a polycrystalline surface. If we zoom in, then we can actually see the individual gold atoms directly in 0.1 molar perchloric acid. And if we zoom out, you can see the electrodes we can use. These are the little bead electrodes that we prepare ourselves in the lab. In situ STM, well, in electrochemistry, we have a working electrode, a reference electrode, and a counter electrode. In so-called normal STM, we have a working electrode or sample and a tip. For proteins, we would like to study proteins in their natural aqueous environment, but we cannot just put water into the STM cell, because then we have no control over what is going on the electrodes. There's no electrochemical potential control. So in electrochemical STM, we combine the two in such a way that we have the working electrode with a potential control relative to the reference electrode, and the tip electrode controlled relative to the working electrode, which is again controlled relative to the reference electrode. So everything is under potential control. And we also covered the tip with an insulating material, except for the outermost tip, with only a few atoms exposed, because they are the ones that carry the tunneling current. If we had no insulating material, then we would risk there would be parasitic Faraday currents that would outwin the tunneling current. In this way, we can look at molecules, some of all the functionalized alkane thiols. This is again cysteine on gold 111, and you can see this is what you would like to call molecular single molecule resolution. Here is on gold 110, where you can even see at high resolution submolecular resolution. Each of these triangles, that is a molecule, and the three lobes are the three functional groups: the carboxylate group, the thiol group, and the amino group. And here some of the very recent data. This is gold 100 that seems to pack in a very strange way in long stripes, which is perhaps surprising, because if one consider the actual structure of the gold 100 surface, there are no indications of stripe formation just from the electrode surface. It is also interesting, the enantiomers of cysteine with L and D give virtually identical packing on the surface, whereas the racemic mixture gives a more rugged kind of packing. It is as if the two enantiomers are somehow in each other's way, and they form kinks and other irregularities. We also have to realize that the alkanes, the functionalized alkane thiols, in this case homocysteine, with one link, one carbon link longer than the cysteine itself, they can also have an electrochemical life of their own. For example, homocysteine displays a very sharp voltammetric peak in the middle of nowhere, so to speak. There shouldn't be a Faraday process at this potential. And we know now this is a capacitor peak again. We can see, for example, if we follow a voltammetric scan, we are far away from the peak. There is largely disorder over the whole surface. Then as we approach the peak potential, we can see that the molecules begin to assemble and form broad areas of highly ordered domains. And they disappear again when you get to the other side of the voltammetric peak. In other words, we see a kind of phase transition. And that means with a phase transition, electrons run to or fro the surface, and the instrument registers that as a current. But it is not a Faraday current, it's a capacitive current. So if we see odd signals, we have to have in mind that the self-assembled molecular monolayers can have such a life of their own. Then we can, if we are lucky, we can see some very pretty surfaces, highly ordered. But what it is that we see is not straightforward. Well, we see blocks, and they are well ordered in different ways. But in order to interpret them, then we need heavy theoretical backup. We need computational efforts. We need theoretical calculations. And then we come up with some sort of not immediately obvious results. If you look at these straight alkane thiols, for example, these two, either the straight or the singly branched, alkane thiol. Then it turns out, if together with our partners, Jeffrey Emels and Noel Hush and their people, if they calculate the traditional structure, the alkane thiols directly on the flat surface, then the electrochemical scanning tunneling microscopy images cannot be reproduced. Reproduction requires a different mechanism. What happens is, there's also experimental evidence for that in the form of fits and vacancies and so on. A gold atom is dug out of the surface. We call it atomic scale gold mining. And then two alkane thiol molecules attack from the side. This costs energy, of course, to take out the gold atom, but the energy is recuperated by the double bonding of the gold sulfur. That is the common mechanism. And in fact, what we are seeing here, this is the first case of atom formation at room temperature. If we compare with the more bulky tertiary butane thiol, there's no room that you can attack from the side. So this is the only alkane thiol that binds directly on a flat surface. So that even though these molecules don't look all that smart, they are smarter than they look like, because they can organize themselves in quite sophisticated ways. Also, if you look carefully, I have to look very carefully, then you see there's a slight zigzag orientation of the individual molecules. That each of these blobs is a molecule. That is not the shaking hands of the researcher. That is reality. These molecules are in fact ordered in that way. It's also nice to see that there are holes in between. Holes tell us how much a molecule, how much space the molecule takes up. The molecule is either there or it is not there. You cannot have a part of a molecule disappearing. So this gives us an indication. Each of these blobs is a molecule. Here is a summary, and we can see all the spake butane thiol, singly branched butane thiol binds exclusively by the atom binding. The tertiary butane thiol exclusively directly binding on the flat surface. If we consider the final butane thiol, that's the optically active, optically active butane thiols. The enantiomers separately, they bind in the same atom bonding, but the racemic, again, as we saw for cysteine, they somehow are in each other's way, so they have to pack differently. Some of them are bound by the atom mechanism, others, as you can see here, others directly on the surface. So here we have a case for the same molecule binding in two different ways on the same surface, and that is unusual. Some similar patterns are encountered if you go to nanoparticles. There are also atom binding patterns. Then we go to a slightly more advanced, we go a step upwards, you could say to more complex molecules, metalloprotein voltammetry at the single molecule level, and in situ scanning tunneling microscopy and atomic force microscopy. Now this is no longer simply tunneling mechanism. For a redox molecule, we have for scanning tunneling microscopy a chip and a substrate, and then there's a bias voltage that shifts the two Fermi levels by the bias voltage energy. For redox molecules, well, for molecules in general, there will be a molecular level, the highest occupied or the low molecular orbital or the lowest unoccupied molecular orbital. For the alkane thiols, these levels are way out of what is accessible. So the mechanism of electron transfer from the tip to the substrate or vice versa is tunneling through the barrier constituted by the highest occupied molecular orbital. But for a redox molecule, this level is much lower. So it is accessible when we change the potential. Here you can see if we change the bias voltage at fixed tip voltage, fixed tip potential, then we change it, we change the substrate potential positively, we increase the bias voltage, so more and more levels become available for electron transfer. And that means the current will rise, as we see it here. The molecular level will also be lowered, but not as fast as the substrate Fermi level. But sooner or later, it will cross the Fermi level of the tip potential, and then a new mechanism will appear. But for the bias voltage, we have to go to very high bias voltages before we will see this other effect. This is clear, more clear for, that is something unique for electrochemical scanning tunneling microscopy. We can either change the bias voltage at fixed potential of one of the electrodes, or we can fix the bias voltage and change the two potentials in parallel. And that would show us, for example, if we shift the substrate and tip potential up and down in parallel, then as we get closer to the molecular level, then the current will begin to rise because the tunneling barrier decreases. But when we raise it far enough, the molecular level is trapped between the two Fermi levels, and then the mechanism changes entirely. Now it becomes hopping, successive electron reduction and reoxidation. In a tunneling language, it is as if we dig a deep hole in the tunneling barrier. So this is a very efficient mechanism, and the current rises drastically. But if we continue rising, sooner or later, still the level is trapped below both Fermi levels, and then the current will decrease again. In other words, we get a spectroscopic feature, and the shape of the band, if you can call it that, well, that depends on the details. It depends on the potential distribution in the tunneling gap. It depends on the ionic strength. It depends on reorganization of the molecules involved. So there's a lot of room for interesting interpretation. Here are some examples. These are earlier examples here, transition matter complexes. And you can see here is the tunneling spectrum. And in the background, you have the cyclic voltammogram on the same molecule. Here are data from Richard Nichols and his people for two organic redox molecules. They show an interesting difference. The tetrathiafulvalene, so-called, has a very sharp maximum, like the one we would like to see. But the floppy Bioelectrochemistry molecule shows a different behavior. It is a kind of sigmoidal correlation. And this will have to be interpreted differently. It is either simple equilibrium, Navier equilibrium between the oxidized and reduced form, or it is gated electron transfer. You will get this kind of behavior if the Bioelectrochemistry molecule has to twist somehow before the electron transfer occurs. And with Richard and his people, we wrote a theory how one could interpret this as gated electron transfer. And it even applies this kind of tunneling spectroscopy to nanoparticles, gold nanoparticles, if they are small enough. When the nanoparticles are small enough, they are no longer like small chunks of gold. They are like molecules that can be successively oxidized up to many different oxidation states. And this is shown here for a 1.5 nanometer gold nanoparticle. This is a differential pulse voltammogram, and this is in situ scanning tunneling microscopy directly in aqueous solution. Still a step further, now redox metalloproteins. We have studied quite a lot, cytochromes, iron sulfur proteins, blue copper proteins. These are very nice data, if we may say so ourselves. Cytochrome B562, studied together with people in Cardiff. David Jones, he can mutate proteins and put cysteines into the protein surface at suitable places. And then the molecule can actually bind directly to gold electrodes, either directly to a single electrode surface where we have nice voltammograms. That is already unusual when you can bind a protein directly to a surface and get good voltammetry out of it. or it can be hooked up between two gold electrodes and give very nice pictures, images, and very nice tunneling spectroscopy. Here, you can see here single molecule resolution for the ferridoxine. And here again, we have blue copper protein azurine. It feels very comfortable if it is immobilized on a self-assembled monolayer of alkane thiol. You can see it responds so nicely with a very pretty voltammograms, and it also gives a tunneling spectrum as we have just seen we would like to see. Still a step further, even more complex molecules. This is now redox metalloenzymes, copper nitride reductase, and you can see there's a copper atom in each end, type 1 copper and the type 2 copper, and it tells anyone, it shouts at you that here is an intramolecular electron transfer channel. The lactases, somewhat similar, there is type 1 center for electron inlet, I think it's sitting here, and then the type 2, type 3 center here, which is the catalytic site. Other enzyme like molecular entities, biomimetic molecular scale, Prussian blue nanoparticles, heme nitride reductase, and ongoing work now with human sulfide oxidase together with Ulla Wollenberger and her team in Potsdam. Some strange issue regarding metalloenzymes. It is common but not universal that the enzymes have no electrochemistry of their own. If there's no substrate, there's no electrochemistry. Substrate, very nice electrochemistry, electrocatalytic electrochemistry. This is reflected in scanning tunneling microscopy. If there's no nitride substrate present, there are no pictures, there are no images. You let nitride in and you get all these nice structures. You can see some of them are even triangular, and that's the way they should look like structurally seen from the end. This is a common observation, and for nitride reductase, it's accompanied by another effect, which was a great surprise to us. If there's no substrate and you scan the atomic force microscopy over the potential range where the enzyme is otherwise active, no change. If you let nitride in, something happens around the potential where electrocatalysis sets in. It is as if the enzyme swells by a whole nanometer. And there must be some sort of conformational change, but the nature of this change is something we have not been able to identify. The same, or rather similar thing with lactase. If there is no dioxidant, which is the substrate here, there are no pictures. Well, the pictures you can see very strangely that the underlying alkane thiol monolayer. And the black spots, that is pits that are always formed when you have gold and sulfur together. Then, and you go to, then you let oxygen in, and you go from the potential where the enzyme is inactive to the potential where it is active. Then all the molecules all of a sudden disappear. It is as if binding of oxygen triggers opening of an electron transfer channel that you can see in STM. And here it is in a different view. Here, no oxygen, then we let oxygen in and all the molecules flare up. And then we try to brush it out again, and obviously we have partly succeeded. This also shows that you have to blow argon in for quite a long time before all the oxygen is out. Now, this was increasingly complex molecules. Now we go to increasingly complex electrode surfaces. And as the first step, we will consider briefly something with gold nanoparticles. As we know, they are common in molecular and biomolecular electrochemistry as catalytic entities. Here is a 3 nanometer gold nanoparticle, 3 nanometers or 2 nanometers. It means that the metallic core is 2 nanometers. As you can see in transmission electron microscopy, that shows the metallic core, whereas in situ scanning tunneling microscopy shows both the metallic core and the coating layer. And quite amazingly, if you insert a 3 nanometer nanoparticle between a redox metalloprotein such as cytochrome C or azarine, you increase the electron transfer distance by several nanometers. If this had been normal molecular material, then the electron transfer channel would completely be blocked. But instead, when it is a nanoparticle, you can see that the rate constant increases by at least an order of magnitude. And that is a puzzle. And we have, and other people that study this, try to find various explanations. Is it a matter of increased roughness of the surface, or is there something else? And we set out to check or investigate whether electronic spillover from a single nanoparticle, could that be a reason for the increased electron transfer rate? Electron spillover means we have at a metallic surface, there is a certain spillover of electronic density. A metallic electrode surface is not just a hard wall. There's a smooth change in electron density from the bulk of the metal to zero sufficiently far away from the metallic surface. If that is different for a metallic nanoparticle from a metallic surface, then there could be a catalytic and inherent catalytic effect. And some data done here at DTU Physics many years ago show that that could be some effect like that. This is the planar gold surface, and this is the metallic nanoparticle. In this case, it is a 309 atom nanoparticle. So it is as if the electronic density expands, and it would expand more the more negatively charged the surface. So we try to calculate electronic transmission in a system like that. We have the molecule, gold molecule that's ferrocene, and then we insert a gold nanoparticle like this. And then we would try to see, can we calculate the electron transfer rate for these two kinds of systems? And what we focused on was the electronic transmission coefficient. This is the current. This is actually the rate constant. You put an E electronic charge in front of it, then it gives you the current. There are web terms, or we can call it double layer terms. Then there's the electronic density of the metal, and then there's the activation free energy, which contains primarily the solvent and molecular reorganization free energy. So what we did was to focus on the electronic transmission coefficient, or if you wish, the electronic tunneling factor. And there are two ways that the electron can get from a donor to an acceptor. If the intermediate states are high in energy, then the corresponding potential surfaces for the donor state and the acceptor state, or the reaction state and the product state, they might be located like this. But then the intermediate state corresponding to electron or hole localization in one of the intermediate groups would be well above the crossing point. So the coupling or the role of the intermediate groups is purely electronic. Whereas if the energies are low, then you have actually physical population of the intermediate state. So you now have a two-step process, something like this. So it all depends on how are the energies of the intermediate state, how do they fluctuate, and do they fluctuate enough so that there can be a resonance between all the three states. Then, so this is the two mechanisms. Then our investigations show the super exchange or the tunneling. Tunneling is also called super exchange, and I am prepared to stand up and defend this is the same as tunneling. That turns out not to be a likely mechanism for various reasons that I can explain given the time. But the two-step electron transfer, that is a possible mechanism. That would be sequential electron transfer from the electrodes to the nanoparticles and further on to the molecule, or the opposite way. And in the steady state, this corresponds to normal consecutive reactions, giving a current form like this one, with the two forward rate constants, and we disregard the reverse rate constants. And if one of them is much bigger than the other one, then it reduces to a single rate constant. So ultimately, what we compare is the rate constants for electron transfer between the nanoparticle and the molecule, or between the electrode and the molecule. And that is summarized here. We calculate the electronic structure. Here is the density of states, and you can see it resembles to some extent what we've seen experimentally. And then we can calculate the electronic transmission coefficients in the rate constants and see what comes out of it. And we can see one thing is that the electron transfer, the catalytic effect, if you call it that, is exceedingly sensitive to the actual surface site of the particle. The particle would have peaks and vertices and facets, and they have widely different effects on the transmission coefficients. And it turns out if we take the most realistic gold nanoparticles of the ones we could calculate, we couldn't calculate anything bigger than 147, then the gold, actually the planar gold, outwins most of the particles, except the gold 100 particle. There you can see there is actually a catalytic effect, if you can call it that. It is not a factor of orders of magnitude. It's a factor of 2 or 3, which is, however, quite rewarding. You can also see it depends on the distance. At some distances, the catalytic effect is larger than at other distances. We also studied the effect of short alkane fire coating, and we found this is competitive, but this is work which is going on. This is unfinished work at the moment. Also, we have to be aware, these are model calculations. The real catalytic nanoparticles, they are very complex. First, they are bigger, and secondly, they are usually covered by a layer of alkane fires. So the conclusion of this is, to the question, can electronic spill over from a single nanoparticle be a cause for long-range electron transfer rate enhancement? The answer is clear, yes, perhaps. Then from single crystal to three-dimensional bioelectrochemical surfaces, and that's what people are very interested in these days. You can say that here you combine what you could call non-traditional electrochemical material science, and you go from pure electrochemistry to applied electrochemistry, and then you are perhaps on your way to sensors and biofuel cells and so on. And what do you expect that porous matrices can give you? Well, it can give you perhaps higher enzyme loading than atomically planar surfaces, because who knows what sort of loading you would have on a polycrystalline surface. And what you can hope for is also higher enzyme stability. And examples are porous metals, gold, for example, and it is various carbon materials, carbon paper, synthetic 2- and 3-dimensional graphene. And in our group, we have been interested in human sulfide oxidase together with Ulla Bollenberger, fructose dehydrogenase, and bilirubin oxidase. And the people in the group who have been prime mover and movers in this, Jing Dong, and Cindy, Jing, Xiaomei, and Christian. Nanoporous gold, this is what it looks like. And this is another way it looks like. And this is a model of nanoporous gold. Well, you can see nanoporous means, some people would say non-crystalline. But you can see it's not as non-crystalline that it really matters. It's in fact locally quite crystalline. This is atomic resolution. And the voltammograms for the gold electrodes, the nanoporous gold electrodes, are quite well resolved, and the different gold facets 111, 110, and 100 can surely be identified. In the way of what we hope to achieve by using nanoporous material, I'll show what one could perhaps hope for. This is a non-electrochemical system. Horseradish peroxidase trapped in mesoporous silica material. Just to show what can happen. If you have the enzyme in solution, that's a certain enzyme activity. Then you heat it to 70 degrees Celsius, cool it down, and measure it again. And then you can see it has somehow destabilized. If you confine the enzyme in the nanoporous material, you can heat it to 70 degrees and you can cool it again and you see exactly the same. So it is obviously stabilized in nanoporous material or mesoporous material. You can also try to destabilize it by adding denaturing agents, urea. If you have no confinement, here you can go up to maybe 1 mole a liter. If you have confinement, then you can go up to significantly higher concentrations. This is something we have studied, comparing single crystal electrodes, gold electrodes, with nanoporous gold electrodes, using different self-assembled monolayers, the different functional groups, and the people who have been involved, particularly Xiaomei and Xinxin and associates. This is the target molecule, target enzyme, fructose dehydrogenase. It contains a catalytic center, FAD center, and then an electron transport channel via 2 heme groups. It can transfer electrons either directly or via a mediator here, ferrocene. And there are ways of distinguishing between, there are ways of calculating how large a fraction of the total active enzyme on the surface transfer electrons directly and how much by mediation. So observations are, here you can see, well, nice quantamograms. They can behave consistently depending on the different lengths of the alkane files. You see this is mercaptor alkanodes in different lengths. And when you see nice quantamograms like this, then you feel inclined to try to analyze them. And we are used to this pragmatic model that's called this, introduced by Armstrong and also used by Kano, that can characterize a number of parameters associated with the immobilized enzyme on the variable length alkane files. And here are the outcomes. You can see 13% of the total active enzyme on the surface of the mercaptor ethanol can transfer electrons directly. And then as the chain length becomes longer, then gradually the fraction decreases very strongly. In comparison, if you use different functionalized groups, different terminal groups, it is obvious that the alkane files, the ethanol derivative, by far outwins all the other functional groups. So, and here are some other outcomes. Here is the current that decays approximately exponential with increasing chain length. Here is the coverage, also strongly decreasing with increasing chain length. And then this parameter beta delta D, that is a measure of the extension over which electron transfer can occur. Beta is the electronic decay factor in the tunneling process, and delta D is this kind of width over which electron transfer can occur. And here you can see the longer the alkane file, the softer is the fructose dehydrogenase bound. You can see this delta D will increase with increasing chain length, and also the lower the coverage, and the slower the process. So these are all for single crystal gold electrodes. If you go to the nanoporous material, then we find there's a higher load and a more facile direct electron transfer. And these two do not necessarily match, because if you go to this different environment in the nanoporous material, the orientation of the molecules can be different. And what we see is, in fact, the kinetic parameters are not all that different. For nanoporous gold, 8.3 versus 7.4 for the single crystal. and the same with the actual rate constant. What is different, however, is the stability, and it is quite rewarding to see that it's not rewarding to see that the half-life was 19 hours on single crystal gold, but it is rewarding to see that it's 150 hours on the nanopolar gold. So this is the sort of maybe results that one would like to see, but maybe more strongly expressed. And one final thing is our ongoing work on human sulfide oxidase in different electrochemical environments. And people involved, yeah, these well-known people. Emil Frøkjær was a bachelor student many years ago, and his data have unfortunately been lying ever since. The common wisdom is, and there's a lot of documentation for that, there is a closed configuration and an open configuration. In the open configuration, the distance between molybdenum and iron is too wide for direct intramolecular electron transfer. But interfacial electron transfer can still be achieved. This is the molybdenum center, this is the iron center, a heme group, and the common view is that the molybdenum domain is attached to a surface, positively charged surface, and then with the iron swinging in and out, the iron domain swinging in and out, and with a certain probability, it will get attached to molybdenum, and the catalytic process can be achieved, can be fulfilled. These are charge distributions that have led to models such as this one. Now, from Emil's and Javed Jan, who was a visiting prof in the group, we could measure the voltammograms first without enzyme, no electrochemistry except for capacitive. With enzyme, there is a voltammogram. And that is quite notable that there is apparently electron transfer also for the enzyme without substrate sulfide. But with the sulfate substrate, you can see there is a much stronger signal, a nice sort of nice looking electrocatalytic voltammogram. Also here we have scanning tunneling microscopy, and here is a tunneling spectrum which has this sort of sigmoidal shape that we have seen before also. And such images, they also give you an indication of how many molecules on the surface are active. Sometimes you find voltammetry that corresponds to a smaller population on the surface than what you actually expected from the amount of enzyme you have put on the surface. And this is usually interpreted as if either you have much less on the monolayer, or as if a lot of the molecules are actually have denatured. If you can combine scanning tunneling microscopy with voltammetry, then you can count the number of molecules on the surface and compare with the number of molecules that will give you the voltammetric signal. We are doing this now for the human sulfide oxidase. We did it earlier for azurine on surface-level monolayers of alkane thiols, and there we found they were all active. Then the Ding Dong's PhD project was dealing with porous carbon materials, exploiting the correlation or the conversion of graphene oxide to reduced graphene oxide, reducing the number of surface functional groups to a minimum. And the idea is graphene oxide is tractable in aqueous solution. It's soluble, whereas graphene or reduced graphene is not. So the idea is you do all your manipulation, so to speak, using graphene oxide. You combine it with molecules in solution, put it all up into your structures, and then you reduce the graphene oxide. Then you have got going also from a less conductive to a more conductive surface material. Oops. Jane could prepare these materials and characterize them with a whole arsenal of sophisticated methods. And here is one example. You can see this is the carbon paper with graphene, and then the increasingly composite material, adding one component after the other, eventually with the actual enzyme. You can speculate, how is this, how could an enzyme be stabilized? I mean, after all, it's hanging onto a fiber. It's not that it is sort of obvious that this should be something that could promote stability. Here is a scheme showing what you are, how these composite surfaces are prepared. There's this polyethylenamine, strongly positively charged. So what Jing would do is you start with the carbon paper, add graphene oxide, and add the PEI. Then she would add another layer of graphene oxide, so that the whole sort of composite would be assembled in this way, and then reduce it electrochemically. So the sort of nice thing about it is, yeah, you can do all your manipulations, all your chemistry, and then reduce and convert it from a more or less insulating to a conducting material. And then you add the enzyme in the end. And here is a cartoon showing what we like to believe is going on. You have a catalysis in the molybdenum domain, and then the electron transfer via this whole interface to the electrode. And here's what you can see. No reduction, that means still graphene oxide, no voltammetry except for capacitive voltammetry. Then you reduce all the graphene oxide to graphene, and then you get rather nice voltammetry. So the voltammetry is, as we can say, for an enzyme, it is quite nice, but it is still problems about the stability. Every time you change the solution, then you lose some of the activity. Whether it is leaking or whether it is denaturation is maybe not exactly clear. You can store it, and yeah, it's still alive after 7 days, but it has dropped quite substantially. And then unless you're going for a biosensor or a biofuel cell that is a one-time use and then throw away, then this has to be improved. On the good side, yeah, it shows quite high activity. These are data from the literature, and that is quite notable about the enzyme activity on the surface, on this particular surface. And also, Jing could also insert this bioanode with human sulfide oxidase into a fuel cell, an actual working fuel cell. And that is what I found quite impressive, that you can actually get a device out of it. That concludes what I had to say. This is the group, and she was not present, and this is Jing Dong in her heydays.
Okay, so thank you very much, Jens, for this very nice report and very nice conference. And really, I'm really greatly confident that this is very interesting for all of us, and especially try to highlight the way we have to investigate effectively the system, electrode and enzyme, let's say. So the first question was from Farhin Zafar. And the question is, will the immobilization of the enzyme be affected by the mode of immobilization? I mean, using sonicator for immobilization or shaker, will it affect the quality of immobilization? So something about the way the enzyme is immobilized physically, or I don't know exactly. So I don't know if you have an answer, Jens, or perhaps you can answer afterwards, I don't know.
I'm sure it will, but sonication, well, we've seen when we're using different, what is a differently functionalized alkane ions, for example, you can often immobilize the protein. Well, you can sometimes immobilize the protein on different surfaces, and then they will show quite different activities. That could be either for the simple redox metal proteins, they will show more or less nice looking voltammetry. Or of course, if it is an enzyme, yeah, enzymes are exceedingly sensitive to the actual surface. So when you say the mode of immobilization, this could be either you immobilize, you try to immobilize in different ways, but on the same surface. Or it could be you try to immobilize on different surfaces. And if it's on different surfaces, then the answer is definitely yes. If you try to immobilize using different pathways, but try to end up with the same kind of immobilization on the same surface, well, then it depends on how sensitive the enzyme is to the different steps that you use. Sonicator, I could imagine, but I don't know. I could imagine this is a bit harsh for the enzyme. So I'm not sure there's a general answer to this or very precise answer, but thinking of what are the local environments of the enzyme on the way to immobilization or after it's mobilized, then the answer is yes.
Yeah, for sure. Okay, so the next question is from Vital Alfonta from Israel. So dear Professor Ulstrup, could you please comment on the relationship of the signals to enzyme orientation on the surface? Are all enzymes oriented in a uniform manner? Also, can you please comment on the possibilities of enzyme misfolding on the electrode surface? And she thanks you for your seminar.
Thank you. The enzyme orientation would almost certainly give different results. If for no other reason, yeah, you have different interaction with surface groups on which the enzyme is immobilized. And secondly, you have this critical electron transfer factor that depends very much on the distance, not only the distance, but also on the actual molecular matter between the active site in the enzyme and the electrode surface. So this is, yeah, the answer, this is what I would say. Whether all enzymes are, what does he say? I think the question disappeared.
What's your problem?
The question disappeared.
Ah.
Is the answer here?
Yeah, the answer disappeared because it was really already asked. I think so.
Yeah, all the enzymes oriented in a uniform manner. I think that is not the case. There is a distribution of orientations. In some cases, with the smaller redox proteins, such as our pet protein, the acerine, it is quite uniform. But for example, with the enzymes, if we use, for example, this an analysis method suggested by Armstrong, then there's always a distribution of orientations. That analytical method is, you can call it crude, or you can call it pragmatic. If you want a detailed model for the orientation, that is exceedingly complex. So it's nice to have a simple model that gives you one parameter, for example, beta delta D. And if you have to assume that beta is more or less constant, then delta D is quite a good practical view of how uniform the distribution is. And then you will see that the distribution is quite different for different enzymes and certainly for different surfaces. For example, in our case, in the cell-based case, she saw a systematic variation of this distribution width with increasing floppiness of the self-assembled monolayer.
Mm-hmm.
And possibility of enzyme misfolding on the electrode surface, yes, I think that is quite risky. If you are not very careful in the immobilization, or if you just dump the protein on a gold surface, then it will misfold. It will partly unfold. So yeah, enzymes already, the small redox proteins are quite sensitive, but the enzymes are much more sophisticated in this respect. So if you happen to do something wrong to them, then they certainly misfold.
Yeah, thanks for this valuable answer. I think that it was also something that T.D. Chung also asked. It was already the same questions. So another question is concerning the use of B-aldehyde or B-functional group for immobilization processes. How we can prove only one tail is involved in bonding with a nanoparticle and the other tail is reacting with the enzyme.
Just a moment, you have to find it.
This is an anonymous researcher.
Or bifunctional group for immobilization.
Yeah, bifunctional.
Yeah. So I assume this has to do with the nanoparticles. So the question is, how can we prove only one tail is involved in bonding with the nanoparticles and the other tail is reacting with the enzyme, so it can be immobilized? I don't know if I have a very precise answer, but if it is a gold nanoparticle and it's a bifunctional linker, then you can choose the linker in such a way that you will know that one end has a very high affinity to gold and the other one affinity to the enzyme. If it is a silyl group, then it binds very strongly to gold and probably not very strongly to the enzyme. If, for example, the two ends would compete for binding to gold, let's say a carboxylate group and a thiol group, then the thiol group would outwin the carboxylate group. So if you first prepare the gold nanoparticles using with a linker or a coating material, then you can be almost certain that it is the sulfur atom which is found, and then the carboxylate or the amino group is ready for binding to the enzyme. Whether you can prove it, yeah, you can prove it in the sense that there are surface spectroscopic techniques that are sensitive enough to tell you what is bound, for example, to the gold surface. So in that sense, you can prove it. It's probably instrumentation that you would call large facilities. So I'm not saying it's easy to prove, but it is provable, I think.
Okay, so there's another interesting question from Alina, who thanks you for the nice webinar. And she has a question about the electron transfer between the electrode and an enzyme through a gold nanoparticle. And how to explain the faster electron transfer through a gold nanoparticle, and can it be explained by a better orbital overlap between the enzyme molecule and the gold nanoparticle, similar to what is observed on roughed electrode surfaces compared to smooth electrodes?
Yes, I think the answer is yes, to the extent I can be sure. We did try to do calculations like that, and we did find a favorable electron transfer between the gold nanoparticle and, well, this was a probe molecule, it was ferrocene, compared to a planar surface. But we also found that it depends very much on the particular surface structure on the gold nanoparticle. Gold nanoparticle has different facets. The gold 100 seems to be the most efficient. There are ridge structures, vertices, and so on, and there are other surface facets, and they were not as effective as the planar surface. Right? This is all model calculations. I also sort of just alluded to these early calculations from DTU physics, where they found that the electronic density spreads out, billows out more widely than the electronic density from a planar surface. So I think there's very much to this question. So very good point.
Okay, perhaps a next question from TD. Can the distance between the gold substrate and gold nanoparticle be finely defined? Because he's afraid that one single aliphatic chain might not be enough to make it constant or predictable.
Let me just see again.
TD Chung.
Yeah. Finely defined, no. I think that say one single aliphatic chain, in our case, that was a model. I mean, if we could, we would have calculated the whole counting, but that was not possible. So at the beginning, so to speak, then we put one ion group on top, and that is rather a floppy kind of molecular entity. It is quite sensitive to whatever is going on in the environment, and certainly, I mean, it is conformationally quite flexible. So if the environment is changed, then you get a different configuration or different conformation. So to answer right away without too much waffle, the answer is no. The distance cannot be finely defined, but it can be sort of defined.
Turning perhaps to nanoporous gold electrode. So a question from Rinat Natsmudinov.
Asmudinov.
Yeah.
We know each other.
So can you read the question? So however, enzymes seem to be too complicated to address the problem of EDL effect on the electrotransfer kinetics in nanoporous gold electrodes. So do you have some experimental data, more simple model like ferritinide and so on?
Well, Renat, the answer is I wish I had. Now the young people in the group, they are sitting and following this. So this can be a very good suggestion to them. We don't have such data at the moment, but of course it's very, very relevant question. We have an unfortunate tendency of loving very much the complex molecules, but we should of course also go back to the simpler molecules.
Okay, so we have at least three questions more related to gold, single gold nanoparticles, SAM and so on, the relationship between them from Professor Xu. So I don't know if you can read them, the effect of SAM, of the movement of gold atom, stability of facet of gold surface, so more related directly on the gold and sulfur-7 monolayer. The effect of the sizes of single crystal gold nanoparticle on the structure of sulfur-7 monolayer, and so on.
The effect of the sizes of single crystal gold nanoparticles on the structures of the same. I'm not sure that anyone really has a good answer to that. There is a size effect, and if I recall correctly, Renate Bielewicz has studied electrocatalysis of different size gold nanoparticles. And your question is, what are the effects of the sizes? As I recall, the effects were rather small, but I had to check with her papers again how small they were. As I recall, it was not a striking effect. So I can recommend that you actually take a look at those papers. They're quite recent, Electrochem and current opinion in electrochemistry. It's very much about the same theme. The effect of gold nanoparticles on fructose dehydrogenase.
So perhaps a last question, because time is running. Or I saw also Ula now who is coming. So where is the question I wanted? Yeah, so the question from Abu Bakar Abdul Salam. Who would like you to comment about the stability and leaching out of enzyme from the electrode surfaces upon repeated measurement?
Is it the top question or is it another question? Yeah, that one.
Yeah.
Stability and leaching out of enzymes from the electrode surfaces upon repeated. Well, the best answer I can give is, yeah, there is some leaching out of the enzymes from the, this is, yeah, well, do you have in mind the nanoporous materials or just any surface?
Well, I don't know.
Right, then I can answer.
It would be quite different. I don't know.
I can say the following. Some molecules, some protein molecules are extremely stable on the surfaces. For example, azurine, again, our PET molecule, you can run many thousand voltammograms and there's no leaching at all. On the other hand, we could see that with, for example, nanoporous carbon materials, there the activity gradually declines, and you can argue, is that because of leaching or is it because of denaturation? If it is leaching, then you could probably detect the enzyme in solution when you believe, I mean, after you believe that the enzyme has actually leached. An established protocol, it is, I can suggest protocols. I'm not sure how established they are. It could be, yeah, as again, you check for the enzyme in solution, see if it is active, or you check how the electrode with the originally immobilized enzyme, how does that evolve in time? Or you could maybe use various surface spectroscopic techniques. Say you could use the electrode for a while and then take it out, dry it, and then use spectroscopy to see if anything has changed. So yeah, there could be protocols, but I'm not sure how established they are.
Okay, so if you don't mind, Jens, perhaps we can ask one more question.
Yep.
Yeah, from Ula. So we found really amazing how well organized are small tiles and how they can form these beautiful ordered structures. And so when combining these layers with proteins, do we have also to consider lateral movement of the modifier molecules or even exchange with solution molecules for the descriptions of processes?
Well, I think you have to consider lateral movements. Again, they look, the molecules look, I mean, the monolayers look quite rigid. I mean, just sort of by inspection. But they are mobile, the molecules are mobile. And if you come in with other molecules, such as enzymes, yeah, then you can certainly imagine that you will change details in the surface structure of the self-assembled monolayers. Exchange with solution, I am less inclined to believe, because even though there is mobility, it is maybe not the kind of lateral diffusion of the thiol molecules along the surface. The binding energy is close to 2 electron volts. So I think it is unlikely that they will actually dissociate into the solution. But surely if you can call it the secondary structure or the structure of the layer could change when you absorb something such as enzymes. I think so.
Okay, so I'm not sure that there are many other questions, because some of the questions I have some difficulty to understand exactly what the researcher wanted to express. and some special questions about cuprous nitrotetracyclase especially, and perhaps you can exchange personally with Felix Ferroni in particular. So if there are no other real questions, I think that we can end up now this webinar, and I would like really to thank again Jens. It was really a tremendous seminar for me, very interesting webinar. And I would like also to thank all the participants for their participation, of course, and for the nice discussion that we had just before. And I hope that very soon we'll be able to have again face-to-face discussion. And I would like to wish you nice days in the future, and of course, very nice scientific results. So, bye-bye.
Merci beaucoup, Elisabeth. C'était un grand plaisir.
Merci aussi.
Thank you for all your talks and everything. Thanks.
Thanks also to you.
My pleasure. Thanks a lot.
Bye-bye.
Bye.